So yes, the topic of today, OpenMP programming, and in particular shared memory parallel programming. And main motivation behind this session, as with the MPI session that was given 2 weeks ago, is that today most parallel applications, for the simple reason that in the year 2000s, CPU manufacturers have run out of room in terms of boosting of the CPU performance, and as a consequence, instead of driving the clock speed and the straight line instruction throughput higher, they turn to other technologies like hyper-threading first and then multi-core architectures. And in HPC in particular, this is crucial to be able to run your application in parallel and so to program in parallel, because in the recent high-end CPUs in HPC that we use in HPC have a very high core count. You have 36 or 64 cores, depending on the vendors. And behind this high core count, there is a consequence is that in order to manage the power consumption, most of the time these CPU with a high core count have a lower clock that the we say consumer CPU. By that, it means that your laptop CPU with turbo boost can have better single core performance than your average HPC CPU. It means that if you want to exploit all these cores, you need to program in parallel. And one of the model is shared memory programming. And behind this, there is the concept of your general HPC cluster with first, if you consider all the compute node, you can program it in distributed memory. But if you limit yourself to a single compute node, you have a shared memory model with all the processing elements. It can be the cores linked to a same memory space and have access to this entire memory space. And so if you want to compute, use the world cluster, you can use MPI. But if you are just interested in shared memory programming, or if you want to do hybrid programming, meaning both shared and distributed memory programming, you can rely on OpenMP, which is an open standard that was introduced quite a while ago in 1997 for Fortran, and then an update in 1998 for C++. And the latest version was released in 2020, in November 2020, which is version 5.1. So what's the idea behind a shared memory system is that you have all your processing elements. It can be just a simple CPUs, if you consider a system with multiple sockets, or it can be your cores or a GPU. And all these cores or GPUs are connected through an interconnect and have access to a single memory space. Okay, so every processing element, whatever it is, have ability to read and write the memory into a single address space and see the memory that has been updated by another processing element. And of course, the reality is way more complicated than that. If you take a real shared memory system, as you have know, most of the time you have a compute node with 2 CPUs, so 2 CPU sockets with multiple cores, and these cores have access to some memory that is closer to them. So you can have caches like the L1 that is just available to the core, and then you can have L3 caches, higher level caches that is available to a bunch of cores, and then you have memory. But the memory can also be linked directly to a CPU socket and not to another, even if another socket can access this memory through an interconnect. You may have different access time depending on how close the memory is. So the general idea of the fact that all the processing element, the cores or the threads, have access to the entire memory still holds, but you may have a different level and different speed of access depending on the complexity of your system. And you have to take it into account. At the end of this session, we will discuss a little bit the effect of NUMA and why you have to take this complexity into account in order to extract the best performance out of your OpenMP code. And most of shared memory programming is done through multi-threading an application, okay? So this is one of the options for shared memory systems, is that using threads that can access the entire shared memory, but these threads can also have access to their own private data. And these threads have their own program counter and thus can follow a different control flow. And the idea is that these threads will be scheduled on your cores. So you have a basic idea. If you take these pictures and you go back to the previous one, basically your threads will be the cores, and then you have the private data can be in a shared memory space or in a cache, and then you have your global memory. So this is the idea behind multi-threading to apply it to a shared memory system. And in this model, as all the threads have access to the same shared memory space, the communication is easier than with other models. If you consider MPI, for example, if you need to pass a message, thread communication and so synchronization is way easier in a shared memory space, where basically threads can communicate by reading and writing shared data stored in memory, okay? So you can basically, if thread 1 updates a value in the shared memory space, then it means that thread 2 can access it and can modify it or use it later on. So no need for particular mechanism for communication, just writing to the memory can make data available to other threads. This is why this is called shared memory. The data is shared among the processing element, i.e. the threads. But of course, when you are in this model, you have the problem of synchronization. When you write and read shared data and that the threads execute asynchronously, you can end up in a situation called a data race, okay? So we need to ensure that the read and the write operation occur in the correct order in order to have correctness of the code, because as the threads execute instruction independently of each other, it means that if you need to rely on the value write by another thread, you need to ensure that these threads indeed completed this work and write the value into memory before reading it. Okay, and so this is the idea of a data race that occurs when one or more threads in a single process access the same memory location concurrently, and at least one of these accesses is a write. And this is why we need synchronization in order to ensure correct time ordering of the memory accesses. Okay, so if we don't do that when writing multi-threaded program, then it can lead to deterministic behavior. Okay, so what is there is different model that you can use for parallelism with threads. You can consider task parallelism, where each task is executing different operations in parallel, and in this model, each of the threads is responsible for the execution of one task. And these tasks may spawn subtasks that also executes in parallel. And the idea behind this model is that you try to identify independent computation, and then you assign them to a task. Another form of parallelism that is the most common and easier to use is considered loop parallelism, where most of the case in scientific application, this is where this is the main source of your parallelism. So you use the loops, and the idea is that you take your loop and you if their iteration are independent of each other, then you can basically split your loop in chunks, and then it becomes embarrassingly parallel, and each thread can work on a portion of the iterations of the loop. So this is the two main sources of parallelism that are available in OpenMP. You can either consider task parallelism, or what we will focus on today, because it's just an introductory course, loop parallelism. Okay, so what we need in order to write a shared memory parallel application, from what we have seen in this introduction, is that we need to be able to create the threads, okay, and specify which data is shared among the threads and which data is private to the threads. And of course, because we are a shared memory space, we need a way to synchronize the threads to avoid data race when accessing shared data. And we need a way to create a task or enable loop parallelism. And all these elements are what is provided by OpenMP and will be the topic of these introductory lectures about OpenMP. Okay. So what is it? It's a shared memory application programming interface. Okay. And it hides the low-level details because, of course, you can enable thread parallelism another way. You can, for example, on Linux or macOS, you can use POSIX threads. And basically, the OpenMP implementation, most of the time, we rely on these POSIX threads. But of course, writing your parallel application with threads and POSIX threads will take more time and needs more boilerplate in order to be efficient and also to be created. And so basically OpenMP hides all these low-level details, okay? And you just have to describe where is the parallelism with a very high-level constructs. And these constructs are compiler directives. So you give instruction to the compiler, and the compiler will transform your code in order to run it in parallel using threads, okay? So OpenMP consists of these compiler directives, but also some runtime library routines to get information about what's the environment and some of the parameters. And you also have a set of environment variables that will modify the way your application will run. So you, for example, you have an environment variables that define the number of threads that you wish to use. Basically, an OpenMP program consists of a base language, which can be C, C++, or Fortran. This is what the binding that the standard define. And then you have annotation, so OpenMP directive that you add to your code in order to instruct the compiler to transform your code to be able to use threads. Okay, and what the directive looks like is that you first start in C, C++ with this pragma keyword, okay? So you have your pragma keyword, and then it's followed by OpenMP to say to the compiler that this is an OpenMP directive. In Fortran, it starts with a comment and then a $sign OMP, which also say to the compiler that this is an OpenMP directive. And then after that, you have some instruction for the compiler, okay? So a directive that describes to the compiler what it needs to do. And optionally, you have some clauses that modify some of the behavior or give extra information to the compiler on what to do. So this is the basic idea of OpenMP. You take your code and you add these directives to it, and the compiler will do all the work behind the scene in order to parallelize your application. Okay, so the advantage of using directives is that you don't really need to modify heavily your serial implementation. If you just don't enable OpenMP, and if your program is well written, then you can still run it as a serial code and just ignore all the directives and run it as a serial application. Okay, if you already have a large code base, then it also means that you can incrementally parallelize your application by adding more and more directive and optimizing a little bit your code along the way in order for the code to run faster in parallel. But basically, if you have a large code base, you don't need to restructure it a lot. You can just add the compiler directive incrementally. And the fact that the compiler is doing all the work is very interesting in scientific computing, because most of the time we are not computer scientists. We are most of the time we have a life science background, and it's easier for us, of course, to just describe what we want to do and let the compiler do the work, and let all the people writing the compiler, the very clever people writing the compiler, do all the clever trick to optimize the runtime and the libraries of OpenMP, and we just have to describe what we want to achieve to the compiler. And of course, it's easier to maintain. This is linked to the fact that you can incrementally add parallelization and disable it very easily if you see any problem. So this concludes the introduction, and now we will dive a little bit more in details about how to go in parallel with OpenMP. Okay, so how do we create or how do we spawn threads using OpenMP? So basically, you write a directive. So you start with pragma OMP or the command $OMP in Fortran, and then you add this parallel directive. And this parallel directive instructs the compiler that at this point you need to create a parallel region, okay, by spawning a team of threads. And these threads will execute in parallel. Okay, and you have optional clauses that describe in more details what you want for this parallel region, and in particular, you add most of the time what type of data are shared or private to each of the threads in the team created for this parallel region. We will go to that right after that. Okay, and then after that, you have a block of code, and this block of code is basically what each of the threads will run. Okay, so you just add this directive, and the block of code that comes afterward is what should be run in parallel. Okay. And in addition to this directive, what is also useful is some runtime function. And this runtime function, if you just use directives, you don't need to include anything. But if you want to use this runtime function, then you need to include some files, and in C it's openmp.h, and in the case of Fortran you use omplib. Okay, and via this runtime you can, for example, inside of a parallel region, determine the number of threads that have been spawned using the OMP get num threads. Okay, it returns the number of threads in the current team inside the parallel region. And if you call it outside of a parallel region, you are on the master threads, and of course it returns only one. There is one threads in the team. This is the master thread. And you can also get an ID, okay, the thread number inside of the parallel region with OMP get thread num. Okay, and it returns 0 if it is called outside of the parallel region. So this function makes sense inside of the parallel region, because basically you need to be in a parallel execution in order for this function to make sense. If you call them outside, it returns 1 and 0 respectively, because you are on the master thread, you are not running in parallel. Okay, and with all of that, we can create OpenMP Hello World. And I don't know why this. Okay, there's some mistakes on the slides. Ignore one of the line. Okay, anyway, we will focus on. So we create the parallel region, okay, pragma OMP parallel, and then we say that we want a private variables, which is thread ID. Okay, and it should be num thread. What happens with this slide? Everything is wrong. Okay, anyway, we get the thread ID, okay, using the OpenMP get num threads. So what is the number of the threads that we are running at the moment? And then we get the number of threads, it is in the parallel region, and then we print that. Okay, and if we want to compile this code, we need to enable OpenMP. And for that, we need to pass a specific flag. So for most of the compilers, you pass it as a -f OpenMP. Okay, for GCC, Clang, as well as the new Intel compiler, this is the option. And for the old Intel compiler, you have Q OpenMP to enable OpenMP. And if you are using the NVIDIA compiler, you can also enable OpenMP using the -mp option. Okay, and this basically said to the compiler, hey, you have to interpret the OpenMP directive. If you don't enable OpenMP, then the compiler will just ignore them. And when you compile this program, for example, with GCC, okay, so you go GCC and you enable OpenMP with -f OpenMP, and okay, the output name of this application will be example, okay, and then we compile the OpenMP hello world, and then we run it, okay, and before running it, we need to tell the runtime environment that we want to run on 4 threads. And this is done by passing an environment variable. So OpenMP num threads equal 4 for in this example. And then we get this result where basically we get 4 outputs for each of the threads inside of the parallel region. And we have a size of 4. So the number of threads that has been spawned is 4. And then we have thread 0, 1, 2, and 3 reporting. And as you can see, the threads are numbered between 0 and 3 in this case. So it starts with 0, and then it goes incrementally, +1 for each of the threads in the team. So the first threads is numbered 0, and the last thread is n threads -1. Okay. And these environment variables that we use in order to define the number of threads, you can set it in a different way. You can export it into your environment so that you can use it multiple times during your session, or you just pass it before executing your application. And another option, if you are running with Slurm inside of a batch job, is that you can use the Slurm CPU per task environment variable in order to set this value, and then you will use the value that you set in your batch script. Okay, so this is an example of a batch script for NIC5. And as you can see, we have defined the CPU per task, okay, to be 4. And this is the value that we will use in this case, okay, by taking this environment variables that is set by Slurm and using it to export it as OpenMP threads. Then it means that we will use the value that we set to CPU per task and to run your application that is launched here. And as you can see, I also loaded the module GCC core also for the running the application, is to make sure that I am indeed using the OpenMP runtime that my application was linked with when I compiled it with the module GCC 10.2. So in the previous example, I set a private variable, which was thread ID, okay? And it means that this variable, we will create a private copy for each of the threads that we create inside our parallel region, okay? And it means that each of the threads adds its own copy of the variable in the list passed to the private clause. Another option is to use shared. Okay, it means that all the threads see the same copy of the variables. And you can also set a default either to shared or known. So by default, the value is shared. Okay, all the variables that are declared outside of your parallel region are set to shared, but you can define the fact that the default value is known. And then if you don't define if a variable is shared or private, then your compiler will complain and say, oh, you need to set it either shared or private depending on your needs. Okay, so this is the way you create kind of private memory for your threads, is by setting the value to private. But in the case of the default value, this is shared, except if you use default equals none, and then the compiler will force you to define explicitly the sharing attribute. Okay. So about private variables, when you privatize a variable, that it means that you create a new variable, okay, and it basically behaves as a new one. It means that it's not uninitialized, so it doesn't take the value that was present in the variable before the parallel region. You create a new one, and it's uninitialized until you do it in the parallel region. Okay. And it also means that this value disappears at the end of the parallel region, okay? and that the original variable is unchanged. Okay, everything that you do on a private variable inside of the parallel region stay in the parallel region, and it's not kept at the end of the parallel region. It means that the original variables that was defined before and then you privatize in the region is unchanged. Okay. If you declare variables inside of a parallel region, this means that this variable is private. Okay. And in C++, to create the variables, this is the default constructor that is called. Okay. If you want to privatize the variables, but you want to keep the initial value, so the value outside of your parallel region, then you can use the first private clause, okay, and then a list of variable, and it means that the compiler will create a new variable, but also initialize it with the value of the variable before the parallel region. Okay, and in the case of C++, when you use a first private, the default copy constructor is called to initialize the variables in this case. Okay, so as I said, by default, all variables are shared, and also all the data that is allocated on the heap. So if you do an allocate or a malloc, these values are shared and cannot be privatized. Okay. So if every time you do a malloc, okay, you are basically creating a shared array. You cannot privatize this value. And of course, when you have this kind of variable, you have to handle them with care. Okay, so this is a very simple example where I create a variable int x, okay, value integers. Then I create a parallel region, and inside of this parallel region, I do a +1 of this value. Okay, and in this case, I define the number of threads to be 2. The problem, if I do that without proper synchronization, is that I can end up with the wrong value. Okay, running this on 2 threads, we can expect before we start to 0, it means that x should be incremented 2 times because we are using 2 threads. So it means that the final value should be 2. But the reality, you can get 1 because you have to consider that the threads are not running asynchronously, and that different order of operation can lead to different results. For example, if you consider x in memory and then thread 1 is loading it, okay, and doing the increment, okay, the memory is still set to 0 because basically the value of x is in a register, and at the same time the thread 2 is loading the value also into a register. Okay, and the next instruction that is executed on thread 1 is store the value of x. Okay, and so the value inside of the register is 1, and this is the value that is put in memory. Okay, but if at the same time the thread 2 is basically incrementing it also, but it has loaded a value that is outdated. Okay, the value is 0 there. So basically, when it stores the value stored in the register of thread 2, then the value is still 1. Okay, and you end up with the wrong result because you are accessing shared variable without proper synchronization, and as a consequence, you get the wrong result. So this is the effect of a data race. What can we do with these parallel directives? Okay, we create a parallel region and we put inside of this parallel region a loop. Okay, a loop that goes from 0 to 1000. Okay, and inside of this loop, the only instruction that is run is we are basically counting the iteration of this loop. And what is the result when we run it? Is that basically, if we run it on 4 threads, we get this result. So the number of iterations that each threads run was 1000. It means that we basically quadruple the amount of work that we did because each of the threads execute the whole loop. There is no loop parallelism. We are not dividing the work among the threads. Basically, all the threads are doing the 1000th iteration. It means that it will take exactly the same time as the serial implementation plus the overhead of creating the thread. So it can be even worse than running it in serial, okay? And this is a very important thing, is that a parallel region is different than a loop parallelism or work sharing or creation of tasks, okay? When you use the parallel constructs, it means that you create a team of threads, okay? And that the code that is in the block is executed redundantly by each of the threads, and the threads in the team join at the end of the parallel region, and you go back to the master thread, okay? But in most of the scientific workloads, we like to parallelize thread loops, okay, and it means dividing the iteration amongst the threads, and we need a way to distribute this iteration, okay? Basically, what we want to do, we have 4 iteration space. We want to divide it in chunks and give these chunks, assign these chunks to the threads. Okay, so in this example, each of the threads will do 3 iterations of the loop. So basically, we divide the number of iterations by the number of threads. And in theory, if we run that on 4 threads, then we get a 4 times speed up, because we have 4 times less work per threads than compared to the serial execution. Okay. One way we can do that is just use the thread ID and the number of threads, okay, and define a lower bound and a higher bound for each of the threads, okay, using this formula. So basically, this is the start iteration of the threads, and this is the upper limit for each of the iteration executed by these threads. And then we store the number of iteration in an array, okay, and each of the threads is just writing to its own space, okay, defined by thread ID. And this is perfectly fine. Doing this, of course, we will divide indeed our iteration between each of the threads, and each of the threads will execute, we do 250 iteration, and we can expect a speed up of 4. But it's quite time consuming to have to think about that all the time and just do a complicated division of the work. And but we are lucky, because basically we already have a construct for that in OpenMP. And what you do is that first you create a parallel region, okay, so you spawn your threads, and then you take your loop and you say to the compiler, hey, this loop can be run in parallel, please divide the work amongst the threads. And to do that, you define your directive, pragma OMP, and then you have the for, and you use the do directive in case of Fortran, okay, and it means you tell to the compiler, hey, you can divide this this loop, and it can be run in parallel, okay? So you don't have to define all the variables that we defined before, and finding the higher value and the lower and upper bound of each for each thread. Then everything is done by the compiler, okay? And it gives exactly the same result as the previous one, but with less code, because basically we let the compiler do the work for us. And in order for the compiler to be able to do that, okay, yes, there is some restriction to the way your loop is written, okay? So basically the loop iterator, so the variables that is used for the iteration cannot be modified in the loop body. It must be an integers. It can be signed or unsigned, it's not important. It can also be a pointer or a random access iterator type in the case of C++. Okay, but start, end, as well as the value of the increment of the loop must be invariant expression, so it cannot change. And the number of iteration must be computable when the loop begins. Not at compile time, it's not necessary, but OpenMP runtime needs at the beginning of the loop to be able to basically split the loop in chunks and distribute the loop to these chunks to the threads. Okay, so it means to be able, when we reach the loop, to divide it. So it means that everything needs to be computable at the loop when the loop begins. What important thing that sometimes you, if you are not careful, you can miss it, okay, is that in order for the loop to be shared, okay, it needs to bind to a parallel region. You need to have a parallel region active, okay, to be able to basically share the iteration of the loop, because in this case, okay, this directive is alone on this, but there is no parallel region. It means that basically you are on the master thread, and what the OpenMP runtime sees is that, okay, there is one thread in the team, the master thread, and I don't need to divide the work because there is only one thread that executes at the moment. Okay, basically you see that only the first thread is running, and you get only the first thread that runs the 1000 iteration. Okay, so you need to create a parallel region in order to use the for construct, because basically if you don't have threads, then there is no division of the work. Okay, and what you can do also is take these two constructs, so the parallel construct and the OpenMP4, and just merge it into one big parallel region plus a distribution of the work. If you only need to parallelize a loop, okay, it doesn't make sense to have to define a parallel region and then divide the work. You can basically just give the instruction, create a parallel region, and divide the loop iteration. And for that, you use the combined construct parallel for. So as I said, it needs to have a parallel region in order to bind, okay, and define the number of threads that are running. But this doesn't mean that you need to have it in the same scope, okay? You can have what is called orphaned directive, when basically the for directive and the parallel directive are not in the same scope, okay? So the OpenMP4 directive is, or do directive outside of the lexical extent of the parallel region. And basically it can be used if you want to have a function that both run in parallel or in serial. For example, okay, we have this function that just multiply alpha by an array by a value of alpha, okay? This is here, and we create an OpenMP4. Okay, and it doesn't like the way it is shown on the screen. It's very nice. Okay, so basically we call this function inside of the parallel region, and the line that you cannot see is when we call the same function but outside of the parallel region. Okay, and the consequences is that, okay, when we call it inside of the parallel region, AX function is executed, okay, by 4 threads, and each of the threads is running on 2015 iterations. So basically, this OpenMP4 directive is binding to the parallel region that we have defined here. If you call the function outside of the parallel region, then the OpenMP4 just bind to the master thread and execute AX on just one thread, the thread 0, the master thread, and do the full iteration space, meaning the 1000th iteration. Okay, so you don't need to create a parallel region exactly in the same lexical scope as the for directive, but of course, if you don't use a parallel region, it means that this OpenMP4 will just run on one thread. You also have an option for loop nest, okay, tightly nested loop. Okay, if you have 2 loops with no code in between, you can collapse these 2 loops in order to increase the trip count. Okay, and you do that using the collapse directive, where basically the 2 loops will be merged, and can be useful if the trip count of your or one of your loop is quite small. Then you can increase basically the iteration space, and you don't have to modify your code for that. You can just say to the compiler, hey, please merge these 2 loops. So we know how to create a parallel region. We know how to divide the iteration of a loop in chunks, and then assign these chunks to the threads, but we can, in some case, change also the way this is done, okay? And this is done using the schedule directive. And basically what you say is that, okay, for this loop, the way you want to divide the iteration is either static, which is the default, dynamic, or guided. And you can also say that I want to define that at runtime, and you can also define a chunk size. Okay, and the value of this chunk size and the behavior associated with it depend on the scheduling that you will use. Okay, So basically the loop static scheduling is what is provided by default, is that you take your loop iteration and you just divide the iteration space by the equal chunk, except maybe for the last threads, because it might run on fewer iterations. Okay, and each of these chunks, big chunks, you assign them to the threads. Okay, and another option is that you want to divide your loop iteration in a chunk size that you define yourself. Okay, so you choose the static scheduling, but then of course you say, okay, I want chunk size of 100, and then the compiler will basically cut your loop in a chunk size of 100 and then distribute it to the threads in a round robin fashion. Okay, so that's basically if you just define pragma OMP4, but you don't specify any schedule, this is what you get. You get a schedule static with the size of the chunks defined by the number of iterations divided by the number of threads. With the dynamic loop scheduling, okay, the iteration are distributed in chunks, okay, and then assigned to the threads. But when a thread finish the chunks that were assigned to it, then he requests another chunks, okay, until no chunk remain to be distributed. Okay, and again, you can define a chunk size optionally if you want. But basically, you just divide your loop in chunks, and then each thread will execute. And when he finishes his work, he asks for new chunks. Okay. And why use dynamic loop scheduling at sometimes is that when the amount of work that each iteration is doing is not constant, you may have some improvement by using this kind of scheduling, okay? For example, if you consider the static way to divide work, okay, each chunk is exactly the same size in this case, but some of the chunks take longer to finish. It may be beneficial to cut it into smaller chunks and then basically run it dynamically, meaning that the threads will execute the chunks and then go back to the runtime and ask for a new one. And it can basically help with load balancing in your for your iterations. So basically balance the amounts of work that is done by each of your threads. Another option is guided, okay, where basically this is the little brother of dynamic, except that the size of each chunk will basically diminish with proportionally to the number of unassigned iteration, okay, decreasing to 1. So you start with a chunk size of, I don't know, 4 in this case, and then it will be 2, and then it will be a chunk size of 1, okay? So this is more, it's exactly the same as dynamic, except that the chunk size is not constant. The less iteration you have, the less the chunk size is. The smaller the chunk size is. Okay. Why using the scheduling clause? Why you need it? As I said, it may help for load balancing, okay? And it's particularly interesting if in the case where the iteration with the I index, okay, is more work. It means that the first threads that are assigned to the first iteration of the loop may finish before the last, okay? We have a load imbalance, the last thread, sorry. So we have a load imbalance. And changing the scheduling in this case from the default static to either dynamic or guided may improve the balance of the work between the threads. Okay, and typical example is when you have a loop that is basically with non-constant trip count. Okay, it may vary because you have an early exit. Okay, that is defined there. It means that this loop will break, or if it's a prime number, it will go for the full iteration space. Okay, so it means that the amount of work that each thread will execute is uncertain. You don't know exactly because basically you have an early exit there. So this loop can be either very long or very short. Okay. So if the number is not a prime number, you have an early exit. So all this iteration will not be run. It means that basically you have not a constant amount of work between the threads. And as a consequence, if you look at this program running with different size, okay, and you have the default time, okay, so this is the column here is the default scheduling, okay, this is static, and then this is static with a chunk size of 100, and then you have the dynamic time and the guided time, and you see, okay, for very large number of very large value, then you have 20 seconds to run, okay, with the default scheduling, the static one. But if you go look at the static with a smaller chunk size, oh, it's way better. Okay, you have about 30% improvement. And the same is true if you use dynamic, that is way better. Okay, it's way better than, it's even better than with a static with a chunk size of 100. And you also have similar result obtained by the guided time with a little bit more overhead here. Okay, so basically you have a very huge improvement in your runtime just by changing the scheduling of your loop. Okay, we go from 20 seconds to 12 seconds by simply choosing to have a small chunk size or by changing the way the loop iteration are distributed. Another case is that when you have a triangular loop, okay, so this number of iteration depends on the value of I, and as a consequence, when you have a large value of I there, it means that there is more work to be done in the inner loop. And you observe a similar result as with the previous example. If you take the default time static, you have 97 seconds for the run, and if you either choose to have a small chunk size or use a dynamic or guided, then you have again about a 30% improvement by reducing the compute time to about 59, 60 seconds. So this was the first part. We have seen how to go in parallel with the parallel directive, and then how to divide the iteration amongst the threads using the for directive, and maybe change the scheduling depending on your problem. If you don't have constant work, then you can change the scheduling of your loop in order to improve. But we have not discussed the topic of synchronization. Synchronization may be needed because, as I said, we have some value that are shared among the threads, okay? And we need to be sure that we have proper time ordering of some read and write for this value. And in some cases also, we need to make sure that a particular operation is only executed once to avoid conflict when accessing shared data. This was what I was talking about before. And of course, ensure a proper ordering of some of the tasks to be executed. So one of the constructs that is provided by OpenMP is a barrier, okay? It's a synchronization point at which all the threads in the side of the parallel region will wait until all the other threads in that section reach the same point, okay? Basically, you have the first threads to arrive at this barrier, we wait, and then you have a second thread that reach the barrier and do the same thing, okay, just waiting. And when the last thread in the parallel region reach the barrier, then all the threads are released and can continue execution. And it can be used if you are basically updating a shared variable, okay, that is used by another thread. In this very stupid example, we are basically considering the fact that we set the value of shared variables, okay, in an array, the value A, with thread ID, and this value will be used by another be reused then, but then we will read the value of neighbors, okay? These neighbors is defined as being or thread ID -1, okay? And in that case, we need to be sure that the neighbor threads set the value before we read it. And so what we do is we put an OpenMP barrier, and this barrier will ensure that all the threads have finished writing the value, and then we can read it safely afterward. Okay, so this is the basic use of an OpenMP barrier. And we have already seen barrier, okay, but this is implicit barriers. So at the end of a parallel region, you have an implicit barrier, okay? So when you start this region, or this region is the parallel one, so it's the code that will be executed in parallel, and at the end of the region, you have an implicit barrier. It means that all the threads need to be finished before we go back to the master thread and then execute the next instruction. Okay, so all the threads will wait at that point. The same is true for an OpenMP for construct. Then you have an OpenMP barrier, implicit barrier at the end of your loop block. Okay, so here also all the threads will wait for the other threads to finish their part of the chunks of the loop that was assigned to them before continuing execution and execute instruction that may be placed there. Another construct is the master one. So you use it inside of a parallel region, and you say that only the master thread, okay, the thread with ID 0 should execute this region. So basically, you have the master thread, okay, and then you have all the other threads, thread 1, 2, 3. And thread 1, 2, 3, we just ignore what is inside the code block assigned to the master section. Only the master will run this part of the code, okay? So basically, it's exactly the same as defining the fact that a block needs only to be executed if thread ID is equals to 1. You can simulate that by just using a if statement and say if thread ID equals to 1, then do that. Okay. And basically what you can do is inside of the parallel region, just change a little bit the hello world example and just do the OpenMP get num threads inside of the master section. And as a consequences, okay, you see that you have all the threads that are not mastered that just print the hello, I am thread, and then the thread ID, but thread with ID 0, so the master threads also print the number of threads in the team. Something similar to the master directive, but with some major difference is the single directive. It means that it's executed only by a code section is only executed by one thread in the team. Okay, only one, but not necessarily the master threads. And the difference with the master directive is that the master directive, there is no implicit barrier at the end of the master. In the case of single, all the threads will wait for the threads that is working on the single section to finish before continuing. Okay, so you have an implicit barrier at the end of a single section. So in this case, this is thread 1 that is executing the single section. Okay, but the master thread and thread 2 and 3 are waiting for these threads to finish before continuing execution. Okay, so basically you put a barrier at the end of the single section. So this is a difference with the master thread. So the master thread is just basically an if statement saying, oh, just execute that if this is the master. The single is a little bit more, involve more synchronization because then you need to add a barrier at the end. Okay, so we can exactly do the same example, this time writing an OpenMP program that say hello world, but with a single section, okay, and we say that it needs to tell that it's in single construct. And in this case, the first thread to arrive to the single is thread 3, okay, and it report that it execute the single construct, but the other threads are not executing it. And also we can see that nothing is printed before because basically the first thread arrives and then all the threads wait before printing the hello world line. Okay, so this is why this line is the first one because it's executed by the first thread and all the threads have to wait before printing the hello I am threads thread ID of end thread. Another synchronization construct is a critical section. And basically, this is a way to exclude another thread from executing a portion of the code. Unlike the master and single section, this critical section will be executed by all the threads. Okay, so it will be executed by all the threads in the team. But when a thread is executing in the critical section, all the other threads are waiting before entering the critical section. So it cannot execute the same portion of the code when another thread is there. So in our example, the first thread to arrive to the critical section is thread 1, and then you have a thread 0, 2, and 3 that execute, but they never execute at the same time. And of course, this is like creating a serialization of your code. So it can have a huge impact of performance if you use this construct too much, because of course, you are basically executing something in serial, but then you multiply this execution time by the number of threads that have to execute the critical section. Okay, and for example, it can be used if you want to compute a sum, okay, and you define a local sum, and then you compute all the local value of this sum, but at the end you want to update the global sum, okay? This is sum. But if you do that without synchronization, you can have multiple threads writing to sum at the same time, and then you can get garbage. So you need to ensure that only one thread is basically executing this instruction, which is the addition of the local sum to the global sum. And to do that, you use a critical section to exclude any other threads to execute inside of this section when we are updating the sum. When you run this code, you have this result where you get all the value of the local sum, and then you see that basically the value of sum is incrementally increasing until you get the final result. What you can do also is name this critical section, okay? Because basically all the threads are waiting at the beginning of a critical section until no other thread are executing this critical section, okay? With the same name. And the problem is that all unnamed critical section map to exactly the same name inside of your program. So, and as critical section names are global to the program, it can lead to basically your thread waiting before entering a critical section that is completely unrelated to what is expected to do. So, for example, here we want to compute a sum and a max, okay? So we are updating shared variable, but they are different. We have sum, okay, and we have max. And of course, it makes no sense for threads that want to compute the max, okay, update the max, to wait in an unnamed critical section that is just updating sum. It will be more interesting to see if you can update max because it's unrelated to this one. So what we do is just name this critical section to ensure that the threads doesn't get stuck because of stupid default name. So basically we have threads that will wait if they want to update the sum, and threads that will wait if they want to update the max value, okay? Another thing that you can do, as I say, is that the Pragma OpenMP4 or critical and even the parallel have an implicit barrier, okay? And what you can do is just remove it by adding a no wait clause at the end of this, because basically when we finish computing our local sum, we don't need to wait for all the threads to finish to basically go to the critical section. We want to update as soon as we get the local sum value, we want to go to the critical section. It doesn't make sense to wait for all the threads to compute the local sum. In addition, if we wait there, then all the threads will try to acquire the critical section. So there is a lot of contention at that part. So it's more interesting to basically lift this implicit barrier with a no wait clause and go directly to the critical section. Okay, so the no wait clause can be applied to remove the implicit barrier for a for directive, and as well as a single directive. If you want, you can remove also the implicit barrier at the end of the single directive. Note that in Fortran, it's not placed at exactly the same place as the C. So in C, it's close to the directive, but in Fortran, you put it basically at the end of the block. Okay, so at the end do, no wait, instead of end do. Okay, so you add it at the end. It makes sense because basically you say at the end of this, this is where the no wait is important in this case. Okay, you have not the curly brace that define the block in Fortran. So basically, you have to define the end of the do directive, and it makes sense to put the no wait there because this is where the barrier is. And why you want to do, you can do is that, for example, you can use a no wait if you have two loops that are basically updating value that are completely unrelated. So in this case, we compute the value of D, okay, with A and B that is used, and there we use A and C, but we don't update A and B as well as C. So basically, these are constant. These two loops, what we want is just write to D and E. And it doesn't make sense to wait for all the threads to finish D before start execution of the next loop. So what you can say is that I don't want to wait at the end. If one thread finish all the iteration that was assigned to him, then go to the next loop and execute it directly. Okay. And then this no wait directive doesn't change a lot of things because basically we end up to this implicit barrier. This is the barrier at the end of the parallel section. So even if you remove the no wait there, all you do is remove this implicit barrier, but you end up in an implicit barrier directly after that. Okay, so in the previous example with the critical, we basically compute a sum. But we do that in a way that is not optimal because basically we can use another construct, which is a reduction. And this construct is there to basically do a sum or a max, a mean, a multiplication or a minus. The minus will disappear soon of the standard. To compute a sum, and the form of this clause, okay, it applies to a parallel or a for construct, is that you use the reduction clause, and then you have an operator and a list of variables that on which this operator apply. Okay, and this operator can be arithmetic, so plus, multiply, minus, max, and min, or logical operator like AND or binary AND or, so you have all these operations available to you. So the idea, okay, is that here we have a sum and we compute also a max value, and we create a parallel region, and then we distribute the iteration of the loop, and we have this sum and max to update. Okay, and if we do that without a reduction or without proper synchronization, we have a data range. Okay, all the threads will try to update this value. And so what we do is define reduction for the sum. Okay, so the operator that we use is a plus because this is what we are doing. Okay, so plus is the operator. In this case, we compute the maximum value. So the operator is a max. So this is the operator max, and then it applies to the variable max. So this is the basic usage of a reduction. That is a very common construct in OpenMP because this happened a lot, that you have to compute a sum, and doing it in parallel is quite useful. So you have a reduction and use it because I mean, this kind of operation has been highly optimized in the compiler. So you can have more efficient code using a reduction than doing the previous example with a critical section. Okay, another type of operation you can do is atomic. Again, it's an operation that is always executed without any other threads being able to read or change the state of the value that is read. Okay, so you have guaranteed that nothing will be changed when you operate on a value on atomic variable. And the basic construct for using atomic operation is pragma OMP, and then you have this atomic directive, and you have some clauses that may apply. Okay, and then you have an expression statement, so an operation that you want to do. okay? And basically the atomic clause describe what you want to do with the variable that is used in the expression statement. You can want to read it, write it, or update it, as well as read it and write it at the same time, okay? And the default value for this atomic clause is update. So the idea is that if you want to read a value, okay, so you want to go to read the value of X and be sure that this value doesn't change between the time at the moment you are reading it. So you want to put it in a V, and then what you do is basically define that you want to do an atomic read, okay? And here you want to update X and be sure that you are the only one to do it at the time. Then you do an atomic write operation. Okay, you assign a value to X. And the update is a combination of the two. And typically this is the type of operation you can do with an update, because in this case, for example, for an increment, you need to capture, to read the value and then update it by doing +1, okay? So this is also true if you do this kind of operation, okay? If you, for example, want to increment X with this kind of operation, this is exactly the same problem. You need to first read it, then modify it, so +1, and then write it back to memory. So this type of operation are called an update, and this is the default in OpenMP if you don't specify any clause for the atomic statement. Okay. You also have the capture, which is basically that you want to update a variable, so capture its value before. Okay, so you want the original value and then you want to update it to memory. So this is the kind of operation that can be used as an expression statement in the case of an atomic capture. Okay, more and more operation, you have a lot of options. Okay, and doing that, even if it's not the best way to do it, you can, for example, just change the critical section of the example with the sum with an OpenMP atomic, where basically we ensure that we are the only threads to modify the value of sum, okay, with an atomic. And as the default is update, and this is typically the operation that we are doing, we are updating the value of sum. We don't need to specify any clause to the atomic construct. So here is another example where we create an array of index, okay, that going to from 1 to 1000, from 0 to 1999. And then we use this array of index to update another array, which is X, okay? And we use an atomic update in this case to avoid any data race, okay? Because basically we are running from 0 to 10,000 in this case, but basically the index that we would use are going from 0 to 1000. Okay, so we may have different threads writing at the same location in X. And the advantage of using the atomic in this example is that it's allow the update of two different elements of X in parallel if it's not the same memory location. Okay, while if we use a critical in this case, it means that basically, even if we are not writing in the same location, all the threads will basically wait for one update to be finished. So it means that this code will perform very poorly and be even worse in parallel than if we do in serial, okay? So the advantage of atomic in this case is that we can basically update multiple value at the same time because we just are interested in a particular index. Okay, we have this is a good way to exclude another threads, but way better than critical. Okay, so In theory, an atomic operation has much lower overhead because it can take advantage of the hardware support for this kind of operation. Most CPU today have support for atomic operations. There is instruction for that. But the set of possible operation that you can do with an atomic construct is very limited. In the case of a critical, then you can execute any arbitrary block of code, but there is a more significant overhead when threads enter and exit a critical section, because there is a lot more synchronization involved, because basically you need to inform all the threads that the critical section is free and that someone can enter, and sometimes with contention that can be very have a very negative impact on the performance of your code. So critical are generic, basically an atomic are low overhead operation, but very limited on what you can do with them. And of course, try to use, and this is the same idea, I say atomic versus reduction is true also with critical versus reduction. Of course, if you can use a reduction instead of an atomic, the reduction is way more optimized. Okay. And in general, when you write parallel code, of course, you want to minimize the use of barrier and critical section, because the critical section, of course, you are basically serializing the execution of your code, and you multiply that by the number of threads. If you have a very large number of threads, this critical section can cost you a lot in terms of performance. And of course, a barrier also, a synchronization point is never ideal. If you see an optimization that can be done by using the no-wait clause, you can try to use it. And also you can, if you don't need any synchronization and just want to execute a block once, but you don't need synchronization, then you can favor the master instead of the single, because the single, there is a barrier at the end, while in the master, you have no barrier. So basically, if you can write your algorithm and transform it so that you can minimize the synchronization needed, do it. It can always be beneficial for the performance of your code. So we'll go quickly to the two last parts of this session, which is first OpenMP and NUMA, and then a small discussion about fault sharing. So what is NUMA? NUMA is non-uniform access, memory access. And this is the memory design that is used in most HPC hardware today. Basically, the access time depends on the memory location relative to the NUMA node. So the reason behind it is that some of your CPU socket may be closer to some part of the memory, or some of your core may be closer to some part of the memory. In the case of, for example, an AMD EPIC CPU, you most of the time run in 4 NUMA nodes per socket. So you may have some of the cores closer to some part of the memory. And the idea is that, of course, if a socket or a core is closer to some part of the physical memory, the access to this memory is faster, okay? So basically a local access is fast, but if you want to access a memory located on another NUMA node, then this is a remote access, and this is slower. For a serial code, okay, if you allocate memory and then you execute it, then all the memory that you allocated, if there is enough space in the NUMA node, then it will be close to the core where you are executing if you have pinned your application, okay? But for a parallel code, and this is for most OS, and this is for Linux at least, okay, it uses first policy, okay? So it means that the array element placed on the NUMA node that you touch first, okay? So this is on the NUMA node containing the core that executes the thread, initializing the value. Okay. So basically what we do here is that we allocate an array A of size n, and then we set the value of this array in parallel, And when we do that, basically we will put the value of A in the NUMA node that is closer to the code that is executing this iteration, okay? But the problem is that, of course, you need to be sure that your thread will not be migrated, okay, that it stay on the same core so that you can access this memory that you have put in a NUMA node close to you. And that you always stay on the same core so that you always access this memory faster. And you have two options for the placement of your threads, okay? You can decide that you want to put the thread far apart, okay? That will improve the aggregated memory bandwidth, okay? As well as the cache size that will be available to your application. But of course, because of that, it means that you may end up with threads on different NUMA nodes. It means that it will decrease the performance of synchronization constructs. A second option, of course, is to put threads very close together, so two adjacent cores. And of course, it will improve the performance of synchronization constructs because you have a huge chance that all your memory, when you touch it in the first touch policy, will be allocated on the same NUMA node for all your threads. And the problem is that it will, of course, lead to a decrease of the available memory bandwidth because basically all your threads are accessing the same memory, as well as the cache size available to your threads. So you have to find a balance, and it depends on the type of code that you have. And so how can you define this? Is that you have two environment variables that helps you decide how your threads will stay and be bind to the cores or the sockets. So you can use OpenMP proc bind, okay, which say that you want to pin your threads to a particular core, and that you want to distribute it either close, okay, so successfully through the available space, or spread, okay, so spread the threads over all the available place, core, or sockets, or threads if simultaneous multi-threading is enabled. And then you have also the OpenMP environment variables that tell you, okay, the core can be placed to a core and can not move outside of this core, okay, stay on a core. Or you can say, okay, I want that the place is a socket, and it means that the threads can basically can be migrated by the operating system inside of the sockets. Another option that is available is the threads, but on the CC clusters, the hyperthreading is not activated, so it's not really useful. Yeah. By default, it goes to cores. But it's not in the standard. So depending on for example, the Cray compiler is basically binding by default. So OpenMP proc bind true. This is not the case with GCC. So depending on the compiler, you may have default binding or not, and it's not really defined. Yeah, basically the place by default is a core, but you don't need to define everything. But I think that depending on the compiler and the runtime, the safe bet is to set the two. Basically, set the place, say what you want, and be sure that basically we bind them a particular way. But I don't remember in the standard if there is a default value, but in my memory it's not, so it depends on the runtime. Yeah.
Do we use that in the CC clusters? You can use that in the CC clusters.
Yes. Yeah. Yeah, it's less important. But it's not, I mean, on most of the cluster, because basically there is one NUMA node per socket on all the cluster except NIC 5, where we have 4 NUMA nodes per socket. It means 8 NUMA nodes per node. And in the case of NIC 5, may have a larger impact because we have so much cores that maybe in some case, if you're memory bound, then it's more beneficial to spread your threads so you get a better bandwidth. But then you need to have exclusive access to the node. good luck with that. The problem with this kind of binding is that it makes sense when you have exclusive access to a node, because you never know how Slurm will try to get, I mean, a block of cores that are close together, but it's not always the case. So all these options only make sense in terms of performance if you are just exclusive access to a node, because there you can really define where your threads are going. If you just have half of a node, maybe you have, I don't know, 2 cores on one NUMA node and the rest of the cores on another one. But most of the CC clusters, we have NUMA active, 2 NUMA per node, because it's basically a NUMA per socket. Okay, another memory effect, which is fault sharing. And to illustrate that, we use simple code that is, again, computing a sum, but this time instead of putting it in a private variable, we use a global one. Okay, we create an array and we basically update only the value that is at the index defined by the thread ID. Okay, and then we do a simple atomic operation in order to compute the final sum. And when we run this code, we try that on 1, 2, 4, or 8 threads. Then we can see that the performance, yeah, we have small improvement when we use 2 threads, but then we can go to 4 and 8. Basically, we have the runtime is higher than when we use a serial implementation, so only 1 thread. Okay, so the speed up between 1 and 2 threads is bad, and when going to 4 and 8 threads, the time spent in the parallel region is worse than with 1 thread. And this effect is due to fault sharing. Okay, basically, it's a performance impact when another thread is modifying an independent variable, but that is located in a cache line. So basically, when the CPU loads value in the cache, it takes it's not loading only one value, it's loading an entire cache line. Most of the time, it's 64 bytes. Okay, so it takes this chunk of memory and move it to the cache. And the problem is that if you update a value, okay, in this cache line and another threads want to access a value or modify a value that is located on the same cache line, but it's not the particular value that thread 0 was updating, you have a flush to memory and then reload of the cache line on core 1 in order to have to be able to update the value in thread 1. Okay, so basically you have the cache that is flushed to memory. It means that if you modify a value in a cache line and want to reuse and want to update another value on the same cache line on another core, you have invalidation of the cache line on this core, and then you have flush to memory and then reload of the cache line. Okay, and the cache line most of the time is 64 bytes. And this is exactly what we see in the case of raw code, because we are basically updating value that are very close from one another. Okay, in this case, we are updating value and it depends on the thread ID. So these values are very close together and probably on the same cache line. And we are updating them a lot because we are in a loop there and there is not so much work to do. So basically we go a lot into this memory location. So we have a lot of invalidation of the cache line. Okay, this is this effect. And this is called fault sharing because basically we don't update exactly the same value, but because there's on the cache line, the CPU considers that they are shared, which is in reality not the case. And what you can do is add an additional padding. Okay, here I do this by defining a line size, okay, that I use to spread the value apart. And when you do that and use a padding of 4 or 8 or 16, okay, 4, exactly the same effect. It's not so great. We have, with 2 threads, we can see that the runtime is higher than when we use only 1. with a slight improvement before, but the speed up is not that great. But then if we use a padding of 8, then we see a major improvement. We see that we have almost a 2x speed up in this case. And with 4, we also have, it's not exactly divided by 2 again, but at least it's improving. And if we go higher than that, we use a padding of 16, we have exactly the same result that we get with 8. And basically, why it works with 8 is that we use doubles, which is 8 bytes, and then we add an additional padding of 8. It means that we get 64 bytes, value that are 64 bytes apart, and so each value is in its own cache line. Okay, so the summary of the force sharing is that when a thread accesses a global or dynamically allocated shared data structure, there is a potential source of force sharing, and it may be difficult to spot because sometimes it's just the stupid thing that your thread is accessing a completely different global variables, but unfortunately relatively close in memory and in the same cache line. Okay, so when it's possible, you can use thread local copies of data, okay, in order to avoid that. And in particular, if you read frequently or modify frequently value inside of the parallel region, it may be very beneficial to have private copy of this value in order to avoid force sharing. So if you do a lot of updates, you may have this effective value close together, and it may be beneficial to simply privatize the value if possible. Okay, and this concludes this introduction to shared memory programming with OpenMP.